Welcome to Math with Professor V. This is video lecture for section 5.4 for business calculus on curve sketching. So what we're going to do in this lesson is put together the ideas that we've gone over in the last few sections, namely finding where a function's increasing, decreasing, its extrema, its inflection points, and then build that or layer that on top of our previous knowledge from our algebra courses to put together a very accurate graph by hand of a function. So here are the steps that are typically included when you're asked to sketch a function's graph. And make note of this list. If your instructor wants you to add or take away any steps, then obviously do what they say, but this is pretty much run of the mill. So the first thing you want to do is determine the domain of the function, determine any intercepts, x and y intercepts. Determine if your function has any asymptotes. So the times when asymptotes will appear are when you have a rational function with exponential functions and with logarithmic functions. If you're a pure calculus student, a STEM major, then you also would add trigonometric functions to this list. But for the sake of business calculus, we don't deal with those kinds of functions. The next thing you would want to do is investigate symmetry. And here's our definition for whether or not a function is symmetric with respect to the y-axis or the origin. Remember, we don't have x-axis symmetry for functions because then they would fail the vertical line test and not be functions. But I digress. So anyways, if f of negative x equals f of x, that's the criteria to determine that the function is even. And then we say we know that the graph is symmetric about the y-axis. So an example of a function that's even, that's symmetric with respect to the y-axis, is our good friend, the parabola, y equals x squared. And you can see clearly it's symmetric with respect to the y-axis, and you can confirm this algebraically. By definition, if f of negative x equals negative f of x, then we say the function is odd, so it's symmetric about the origin. Very common function, if you want to just have an example in your head for an odd function, symmetric with respect to the origin, is y equals x cubed. If this is a topic that you're a little bit rusty on, don't worry. I have a few videos, I think parts 1 and 2, showing how to test algebraically whether or not a function is even or odd. Okay? Good, so this one's odd, symmetric with respect to the origin. This one's even. No coincidence, 2 is an even exponent, 3 is an odd exponent. But when there's more terms or, it's a rational function, it gets more involved to check. I'll show you. Okay, this is all review stuff. So these topics basically are from before you started business calc. Now, the rest of the steps in curve sketching are the things that we've covered in this course together. So step 5, you want to determine the intervals where f is increasing or decreasing. In order to do that, you need to find f prime first, right? Then find your critical numbers. And then from there, you could figure out where the function is increasing and decreasing. Step 6, you want to determine any relative extrema, so relative mins and maxes. You can use either the first derivative or second derivative test. Since in the previous step we're finding where the function's increasing and decreasing, we're going to use first derivative test for that. That's probably what we're going to do for the majority of step 6. Then you're going to have to determine the concavity and inflection points. So again, remember, in order to do that, we need to find f double prime, set it equal to 0, and then find where it doesn't exist. And then we can determine the concavity and inflection points. So this is all the new stuff from calc. And then step 8, you just put everything together. So all of the important points that you found from steps 1 through 7, you're going to graph them. So you're going to plot the intercepts, critical points, inflection points, asymptotes, whatever else. If you're still nervous, you just plot however many points your little heart desires till you feel good. And symmetry can be helpful because then you can just reflect a huge chunk of your graph and not have to worry about what it looks like in certain places. And then draw it nicely, smoothly. Do your best using the correct concavity. And I'll help you. I'll walk you through the process. That can be a little bit scary. And then at the end, you're new at this, so check it using a graphing calculator. I recommend going to desmos.com. They also have an app. and you can verify that you graphed correctly. Not that you'll be allowed to do so on an exam, but it just gives you an idea, okay? All right, let's hop to it. I've got 2 examples. Nothing excessive. So we're going to use the steps outlined above. Let me scroll up so you can take a screenshot of all of the steps. Got it? Because I'm just going to refer to them. Okay, here we go. So f of x is x cubed minus 2x squared. So first thing, we're going to find the domain. It's all real numbers because it's a polynomial. That's good. Second thing, we need to find the intercepts. So let me find the x-intercept first. You do that by setting the function, or y, equal to 0. So 0 equals x cubed minus 2x squared. I can factor out an x squared from both of the terms, and then I have x minus 2. So x squared in the front tells me that x equals 0 is where one of the x-intercepts is, and the other one is at x equals 2. And write these as ordered pairs. That way you remember that they're actual points on your graph. So you don't get them confused with asymptotes or something. Okay, so these are our x-intercepts. And you know what? We got a bonus because 0, 0 is also my y-intercept. So we don't have to do anything else to get the y-intercept. You could also tell just by looking. If you plug in 0 for x, your y-intercept is 0 also. Okay. Next thing, let's just check any asymptotes. No, it's not a rational function. It's not an exponential function. Not a logarithmic function, so we're good. Polynomials don't have asymptotes. Now I want to check for any symmetry. So here's this process. You always substitute in negative x for x into the function, and you simplify. So this would be negative x cubed minus 2 times negative x squared. So this will be negative x cubed minus 2 times now positive x squared. Okay, that's simplified. Now what I do is I compare this result with the original function. If it's exactly the same as the original function and nothing changed, that means f of negative x equals f of x and my function's even. If it changes by getting multiplied by a negative, so if it's the opposite of my original function, then we say f is odd. So is it exactly the same as the original? No, we have a minus sign on this x cubed. Is it the opposite of the original function? Did everything get multiplied by a negative? No, this one didn't change. So this one is neither odd nor even, so we have no symmetry. And like I said, I'll link a video here. Just click in the top right. If you need to practice determining algebraically whether or not a function is even or odd, I got you, because this is something maybe you've forgotten how to do in a while. No big deal. Okay, step 5, now we have to determine intervals of increase and decrease. So in order to do that, let's take a derivative. F prime of x is going to be 3x squared minus 4x. And then we need our critical number. So I'm going to see where does f prime equal 0 and where f prime of x does not exist. So if I set the derivative equal to 0, I'm going to have 3x squared minus 4x is 0. I can take an x out, and then I just have 3x minus 4 left. So either x is 0 or x is 4/3. And then there aren't any places where the derivative doesn't exist. It's also a polynomial, so domain's all real numbers. And these are my 2 critical numbers. Okay, so now let's do the first derivative test. We're going to make a number line. Label it f prime. This is for the first derivative to determine where the function is increasing and decreasing. So here's 0 and here's 4/3. Okay, so if I substitute in something smaller than 0 into the derivative, you can plug it in here or here, say -1, then it'll come out to be positive. So that means the function's increasing there. If I substitute in something between 0 and 4/3, say 1, that would be 3 minus 4, so that's negative. So my function's decreasing. And something bigger than 4/3, the derivative's positive, so the function's increasing. So now we can answer this portion of the question. So we can say our function is increasing on the interval from -infinity to 0, union 4/3 to infinity, and it's decreasing from 0 to 4/3. Beautiful. Okay, step 6, we need to find any relative extrema, relative or local mins and maxes. So clearly I can see both critical numbers are relative extrema. At 0, we have a max, so I can say relative max, and let's just be thorough. I'll write f of 0, which we already know is 0. Remember? Oh yeah, we have that one. That one's easy. And then 4/3 yields a relative min. So relative min is at f of 4/3. This is going to be a little more tricky to find. Remember, when you're getting the y values for your extrema, your inflection points, whatever, you always plug them into the original function because you want to know where they are on the actual graph. Okay, so that's why I'm going to plug in 4/3. So this is 4/3 cubed minus 2 times 4/3 squared. So this is what, 64 over 27 minus 2 times 16, that's 32 over 9. And this comes out to about negative 1.185. Because we're going to be graphing it anyways, right? So it's helpful if you have a decimal. Just ask your instructor. Usually you should give one exact answer, and then you can do the decimal to help you graph. So 64 over 27 minus, this would be 96 over 27. 64 minus 96 gives me negative 32 over 27. Yeah, so if you want to give it exact, you could say the min is at 4/3, negative 32 over 27. Okay? But for our purposes, when we're plotting, I'm just going to think of it like negative 1.2, basically. Okay, very good. That's thoroughly answered. Moving on, part 7, we need the second derivative. So where'd my first derivative go? Here it is. Let's fetch it so we can figure out our intervals of concavity. Let's take one more derivative. So f double prime of x is going to be 6x minus 4. And then what do we do from here? Well, we find where the second derivative is 0 and where it doesn't exist. So there aren't going to be any places where it doesn't exist. But if I set it equal to 0, that means 6x minus 4 is 0, which means x equals 4 over 6, which is 2/3. Okay, so now we make another number line. I'm going to put 2/3 on there. Label the number line f double prime. That way when you're testing, right, you remember, oh, I'm plugging it into the second derivative. So say I pick something smaller than 2/3, like 0. 0 minus 4, that's going to be negative. So my graph is concave down on that interval. And then something bigger than 2/3, like 1 or 100, second derivative is positive, so it's concave up. So now we're ready to answer step 7. The graph is concave down from negative infinity to 2/3 and concave up from 2/3 to infinity. Very good. Do we have any inflection points? Yes, at 2/3. So f of 2/3 is going to be 2/3 cubed minus 2 times 2/3 squared. I'll give the exact answer and then a decimal approximation. So this is 8 over 27 minus 8 over 9. So times 3, that's 8 minus 24 over 27, which is negative 16 over 27. And that's as reduced as it gets, which is approximately negative 0.593. Okay, so keep that in mind. That way when we graph it, we'll be ready to go. We have to put all of this together, and now we're ready. Okay, so let's just make a list. I usually like to just put together everything that I have from the beginning. So we have intercepts 0, 0, also 2, 0, and then we had a max at 0, 0, relative max, and then we had a relative min at 4/3, negative 1.2. I mean, if we're being honest, no one's going to notice if it's negative 1.185 or negative 1.2 when you're graphing. That's certainly good enough. And then we have an inflection point at 2/3, negative 0.6. Okay. All right. So then I'm just going to scale things pretty spread out. None of the values are very large, right? So here we go. Here's the y-axis. Here's the x-axis. Make sure you label those two. And I'll go out to 2. 1, 2. 1, 2. Okay, so let's start filling everything in. So 0, 0, 2, 0. This is also a relative max. Let me write that there to remind myself. 4/3, negative 1.2. So that's like 1 1/3, negative 1.2 around here. That's a min. And then we have an inflection point at 2/3, negative 0.6. That's an inflection point. Okay, so this is all going to come together. It's just a little scary right now. What I want you to remember is the graph, the concavity really helps you. The graph is concave up from 2/3 onward. So from 2/3 onward, it's concave up, and this is a min. So you're basically going to make it look like a parabola opening upward from here to the right. I think you guys can do it, right? Yes. You're like, we got this, Professor V. And then nobody cares what happens over here. There was no interesting information, so you just put an arrow on there and you mind your business. Now, if this is the inflection point, it's concave up here, it's concave down the rest of the graph. So it has to slope this way, curve this way. This is the max. So you make it look like a sad parabola the rest of the way. Don't go higher than that, that's the max. And then, like I said, no one's really interested or stressed about what happens over here. So you just make sure you put the arrow. And that's it. And I think it's helpful, label where the inflection point is, just in case you don't nail it, with your graphing skills. Everyone's on different levels. It's okay, but do your best, go slowly and care, okay? And then they'll come out decent. All right, shall we try one more? Yes, we have to take up the difficult level just a wee bit, right? The difficulty needs to increase. So here we go. Graph the following functions using the steps outlined above. F of x is negative 2x over x squared minus 4. So I want you first, let's factor the denominator, because remember, we need to find the domain and all that stuff. And since we have a rational function here, we have to pay attention. Okay, so step 1, the domain. Clearly I can see x can't be 2 or negative 2, because then the denominator would be 0 and the function would be undefined. So x such that x can't equal plus or minus 2. Okay, now it's time to find the intercepts. So x-intercept, you can find by setting the whole function equal to 0. Shortcut for a rational function, you just set the numerator equal to 0. Done. And then that's actually also the y-intercept, if you think about it, right? If I substitute in 0 for x, anytime you have 0, 0 as an x-intercept, it's also the y-intercept. You can never have more than one y-intercept, because then it wouldn't be a function. You wouldn't be graphing a function. And these are all functions, okay? You can have more than one x-intercept, but not more than one y. Oh, no, no, no. Okay, any vertical asymptotes? Yes, precisely where the denominator is 0. So remember, we write the equation of a vertical asymptote as x equals something. So they're at x equals 2 and x equals negative 2. That's why I make such a big deal that you don't write your intercepts as like x equals 0, so you don't get it confused with your equations for your asymptotes. Always write your intercepts as ordered pairs so you remember that they're points, okay? And then the other thing we have to find are any horizontal asymptotes. And remember, we find those by looking at the end behavior of our function. So we're going to look at the limit as x approaches infinity. Yes. So we have negative 2x. I'm going to use the OG version before I factored, over x squared minus 4. So divide by the highest power of x in the denominator. We're dividing by x squared in this case. And then let's simplify and see if we can evaluate this limit. So this is the limit x approaches infinity, negative 2 over x over 1 minus 4 over x squared. And then as x approaches infinity, we know 2 over x, that's going to go to 0. So is 4 over x squared. So I'm just left with 0 over 1, which is 0. Good. And then usually we also have to check what's the limit as x approaches negative infinity. But while working through this limit, it didn't make any difference whether x was getting very, very large in the positive or negative direction. The outcome is going to be the same. So I'm just going to put a little plus or minus so I don't have to redo the steps, because nothing would change if x went to negative infinity instead. So once you get the value from that limit, then that gives you the equation of your horizontal asymptote. But remember, it's y equals whatever you got. So y equals 0. Good? Okay. Now let's check symmetry. So remember, you substitute in negative x for x. So f of negative x would be negative 2 times negative x over negative x squared minus 4. And then simplify, so this is positive 2x over x squared minus 4. And I'm trying to compare this with the original function, which was negative 2x over x squared minus 4. Well, it's definitely not exactly the same as the original, so I know it's not even. You see how the minus sign went away? That tells me this is the opposite of my original function. If that's hard for you to see, just think of it this way. This is negative 2x over x squared minus 4. And this right here is f of x. So this is negative f of x. So we just showed f of negative x equals negative f of x, which is the definition for a function being odd. And if it's odd, then it has origin symmetry. Okay, that was thrilling. And that's all for the background. Now we get into the calculus. So here we go. We need to find the first derivative, f prime of x, so we can find critical numbers. It is time to use the quotient rule, my friends. So here's f of x. You ready? Okay, so we've got, come on, straighten up, please. Beautiful. Low, d high, minus high, d low, derivative of the bottom, over low, low. Good. You could factor, but it's not bad if we just distribute. So let's just distribute. I feel good about it. So this is going to be negative 2x squared plus 8 plus 4x squared over x squared minus 4 squared, which gives us 2x squared plus 8 over x squared minus 4 squared. Fab. Okay, not too bad. Now we want to find critical numbers. So I want to see, where does f prime of x equal 0 and where does f prime of x not exist? Okay, so it equals 0 if the numerator is 0. Remember our little shortcut, which would mean x squared is negative 4. Well, that's not possible. No real solutions there, so none. And then f prime doesn't exist if the denominator is 0. Well, that happens if x squared minus 4 is 0, if x equals plus or minus 2. But remember, those are not in the domain. So I have no critical numbers. How sad. Okay, it's fine. We'll deal. No critical numbers. I still have to do the first derivative test to see where the function's increasing, decreasing. And remember, when you have vertical asymptotes, you do put them on here, but you put dashed vertical lines or whatever's going to help you remember, hey, these guys are not in the domain, but I have vertical asymptotes there. I still have to check the sign of the derivative on either side. Okay, it's like hot lava. Don't touch this. Okay, here's my derivative. Did you forget? Here it is, f prime of x. I want you to notice something about it. The denominator is squared, so the denominator is always positive. And then the numerator, x squared, that's positive. If I add something to it, it stays positive. So f prime of x is always, yes, positive. So I don't even have to plug anything in. I just go, it's positive. That means my function's increasing. Hooray. But you have to write your answer with so much caution because you have to skip over the places where the function doesn't exist. You have to skip over the domain restrictions. So don't get too excited. It's increasing. Don't say negative infinity to infinity, right? No, no, no. From negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Got it? Yeah, we got to skip over those problem areas. And then decreasing nowhere. I mean, we don't have to write that, but let's do it. Any relative extrema? No, because it never switches from increasing to decreasing. So no relative extrema, no relative mins or maxes or whatnot. Okay. All right, moving on, we need our inflection points. So we need to take the second derivative. So I'm going to come over here, snatch that little first derivative so we can use it. And you're right, we need to do one more round of the quotient rule. So this is f prime of x. Okay, f double prime time. So we've got low, which is the denominator. D high, derivative of the numerator is 4x. Minus high, the numerator. D low, you got to do the chain rule. Please be careful. You bring the 2 down front. You have x squared minus 4 to the first. And then derivative of x squared minus 4 is 2x. Over low, low. X squared minus 4 to the fourth. Okay, from here, don't multiply the whole thing out. You'll lose your mind. Look at these two terms in the numerator. What can I factor out? I can take out 4x and 1 factor of x squared minus 4. So if I take out 4x and one of these, then I have x squared minus 4 to the first left, minus, and remember, I took out 4x, so that's gone, that's gone. I just have 2x squared plus 8. Make sure you keep the parentheses. Over x squared minus 4 to the fourth. Fabulous. I can cancel now. Hooray. And then I only have 3 of these in the denominator. So then this becomes 4x times x squared minus 4 minus 2x squared minus 8 over x squared minus 4 cubed. And then at long last, f double prime of x is 4x times negative x squared minus 12. You know what, guys? No, we can't leave it like that. It looks so ugly with that minus smushed inside. Factor the negative out and write it as negative 4x times x squared plus 12, over x squared minus 4 cubed. That's much better. Okay, did you make it? Hang in there. So now we're going to see where the second derivative is 0 and where it doesn't exist. So f double prime of x equals 0. F double prime of x doesn't exist. It's 0 when the numerator is 0. So either negative 4x is 0 or x squared plus 12 is 0. Negative 4x is 0. That just means x is 0. X squared plus 12 is 0. That means x squared is negative 12. No, that's not possible amongst the real numbers. And then f double prime doesn't exist. Again, that happens when the denominator is 0, which happens at plus or minus 2, but those are not in the domain. I am going to put them on the number line, though, just so we check the concavity on either side of the vertical asymptote. Asymptotes, excuse me, we got 2 of them to be on guard for. But don't forget zeros going on there, okay? And then these 2, can't touch that. My high school pre-calc teacher, when we were learning vertical asymptotes, he would say, oh, they're MC hammer, can't touch this. But you guys are probably too young now to even know who that is. Okay, so let's test the sign of the second derivative. Here it is, okay? If you pick something like negative 3, this is negative. This is always positive. 9 minus 4, that's positive. So what did I say? Hold on, I have to think. -3. Oh, -3 times -4, that's positive, positive, positive. Okay. So second derivative is positive. The graph is concave up. Now -1. -4 times -1, positive, positive. But 1 minus 4, that's negative. Okay, so second derivative is negative here. How about +1? Negative, positive, negative. So negative over a negative is positive, concave up. And then if I pick something bigger than 2, like 3, negative, positive, positive, so it's negative, concave down. Okay, very good. Just wanted to get through that part quickly because I figure you guys are tired, but if you need to go more slowly and write it all out, have at it. No one will be angry with you. So let's see, the graph is concave down from -2 to 0, union 2 to infinity. It's concave up from -infinity to -2, union 0 to 2. Do we have any inflection points? Only at 0. Remember, we have asymptotes at 2 and -2. So we do have an inflection point, f of 0, which is 0. Okay, what else did we find earlier? Nothing interesting, right? The function's always increasing. We have horizontal asymptote, vertical asymptote, and an x-intercept at 0, 0, which we just found again to be our inflection point. So not much I need to bring down from the beginning of the problem. But just reference your work. We're ready to put a graph together, believe it or not. Believe it or not, it's happening. Okay. So all the action's happening at those vertical asymptotes, let me tell you. So put them in. You don't need to scale your graph to 10. Nobody cares what's going on out there, you know? So you live your life, you scale how you see fit for the problem. Just gonna leave it. I like it, it's great. Okay, so we've got an inflection point here. F of 0 is 0. And then we're just gonna use the concavity to help us put it together. And remember, it's always increasing. Good. The graph is concave down. Concave down over here. So you only have two options. Either it looks like this or it looks like this. Which one's concave down and increasing? It's this one. This is concave up and decreasing. Totally wrong. Okay, so concave down, decreasing. And you might say, but I don't know exactly like what the points are. Nobody cares. You want to plug in 3 so you have like a nice point, you go for it. It's not necessary though. Okay, between 0 and 2, it's concave up. Concave up. This is concave up. It can't be like this. That's concave down. Concave up. And then that's an inflection point. So on the other side, it's concave down. Concave down would look like this. So it looks like x cubed smashed in the middle. Yes? And then we know we have symmetry about the origin. So if we have this portion down here below, it should be reflected above, but let's confirm. Yes, the graph is concave up. So you have two options. Either it's here or here. Which one's concave up and increasing? This one. Okay. So let's just graph it in there. We already had a feeling based on symmetry and so many other factors. And there's our graph. You know what? I just hate how wiggly that one is. I'm not proud of it. Okay, that's better. What do you think? Does yours look better? Comment down below. It probably does. Or maybe not. So that concludes the lesson. I only did 2 because you can see they take some time, don't they now? But if you're just like, I need more examples, this wasn't enough, I'll link a few videos in the description. However, they're graphs that I've done for like STEM major calculus. So if some of the functions are too difficult or they involve trig, just skip them. But if you just want more like rational functions where there's asymptotes, I totally get it, that those can be tricky. So I have more examples if you feel like you need to watch more. Okay, that's it. So hope you enjoyed the lesson. Don't forget to give the video a thumbs up, subscribe, and follow me on Instagram and TikTok. You know what to do. Math with Professor V. Keep up the great work. You guys were almost in the home stretch.